So, welcome back once again. Now today we extend what we have done in the last 3 lectures to the case of a rectangular loop in a uniform magnetic field. And we'll see that the loop will experience torques which will rotate it and generate things which are of use to us, and we'll see that. The torque on a current loop, and we define what is known as magnetic dipole moment M, which is similar to the electric dipole moment P that we had between two charges minus Q and Q, and running from minus Q to Q. This was equal to the separation between the two charges multiplied with the charges. And here we will find that the magnetic dipole moment of loop, whatever shape, not necessarily rectangular, this is given by the current flowing through it multiplied by the area of the loop. We will see in the due course of time. So what we do is we place a rectangular current carrying loop carrying a current, steady current value I, and we put it in a uniform magnetic field, and thereby we are going to define the torque that will obtain in that case. Okay. This uniform B we have generated from the north pole to the south pole, okay, of maybe a horseshoe magnet or maybe any arrangement which we will not concentrate right now. Right now we think that the loop A, B, C, D, A, okay, this contains, this is a loop and which is placed in the uniform magnetic field produced by the two poles north-south. AD and CV or AD and BC, they are equal to A, and AB and DC or CD, they are equal to B. So that because it is rectangular, therefore A into B will be equal to the area A, and we know that the surface area is a vector element. That we'll talk when we go. Now look here. In the first instance, we put the loop in the plane of the boat. The magnetic lines of field or the magnetic field is also along from north to south, okay, which has been shown as this. Okay. So you can see that there are various sectors, and according to the rules of the game that we have learned about the lengths of current carrying conductors, experiencing force B will exert no force on the sectors AD and BC. Why? Because the current is in the direction of the magnetic field. Okay, if the current is in the direction of magnetic field, and I can show it to you that the magnetic field is the current, for example, over here is like this, and over here it is like this. And if we use the right hand palm rule, okay, then the magnetic field direction is like this, okay, and the direction of the L is also in the same direction. So L cross B will be equal to 0 here, and L cross B will also be equal to 0 over here, because of the wire carrying current being parallel to the field. Now let us say that on this part A to B there is a force F1, and on this part from C to D there is another force which is equal to Bf2. We can write the force value as I L cross B, okay, and of course the angle is 90 degrees, therefore F1 will become equal to I B into P. That same formula, ILB, force is equal to ILB, which I which my teacher used to call bill. Okay, so this bill gives IBB. And similarly, in the second case, the force is IB cross B, okay, L cross B, and the magnitude turns out to be equal to IBB again. So this has been shown over here. The two forces, one is going down and the other force is going up. So I can write that the two forces are equal and opposite to each other, okay, and therefore we can write the sum of the two forces is F net is equal to 0, that is the net force acting in this system is equal to 0. But although the net force acting in the system is equal to 0, there is a torque, okay, and the torque can be measured as just I am writing the magnitude. The torque that will happen over there is F1 into A by 2. This is A by 2, okay, and F2 into A by 2. This is also A by 2. So I can write the magnitude from here, IBB A by 2 plus IBB A by 2. That gives I AB into B, okay, where AB is equal to the area that we have over here, and so I get this value as IAB. Right? Now we have a definition, and we define that since this area is a vector, okay, for the reasons we have discussed before, but I am going to tell you again that area actually, if I have one length x, another length y, I am taking a rectangular case, I have one vector x and another vector y, what happens when we complete the parallelogram? I get a rectangle, one thing, and then when I say that I am taking x towards y, the first vector towards the second vector, then my thumb is outcoming, and therefore this is the direction of the surface area of this thing. So therefore a surface area as it is a scalar, but the surface area is a vector. That should be borne in mind, that the argument you should be able to give readily to another person who is contesting you that area is not a vector quantity. Then tell him or her that this is how the area is a vector quantity, because the distance x is rotated towards the distance y through the smaller of the two angles. That the second vector makes with the first vector, and that is 90 degrees. Another angle is like this, which is a larger angle, and we abandoned it in favor of the smaller angle. Okay friends, so I get, there is a definition, IA is equal to M, vector M, which we call the dipole moment vector, okay, magnetic dipole moment vector M, okay. So this is the definition, and now we will tilt it a bit, okay. We will tilt it because right now this is like this, and now I'll show you as to what happens when it is tilted like this. This is rotated along an axis which is midway through it, and we rotate it the way it has been shown with an angular velocity omega. So I do that. So we did it for a rectangular loop, and that loop was in the plane of the board. So it's the angle between the area that creates AB and the magnetic field, that was pi by 2 radians, for which sine of the angle sine theta is equal to 1. So we obtain things like that. Now I am sort of tilting it. Okay, this was the situation of the board, and now we are tilting it like this. Okay, or like this. Okay, so our area vector that makes an angle theta with the B. This is the situation which we'll encounter in general, and of course F1 and F2, which are the forces on AB and this and this, okay, where the value is IBB. In fact, the formula is ILB, or Bill sine theta. Okay, and the net value of the force is equal to 0, because F1 vector F1 is equal to minus times vector F2. Now, normally the net force vanishes, but the forces F1 and F2 are not in the same line. They are not collinear. So that gives rise to a situation of a torque. And like we did earlier, now earlier it was F1 into A by 2, so I am adding sine of theta, and F2 into A by 2 I am adding again sine theta, and sine theta fluctuates between